What if the most valuable factories of the future weren't on Earth? Most people think of space as a place for rockets and exploration, but today's guest sees something very different, a supply chain in orbit. Reditus Space is building reusable satellites to make zero-gravity manufacturing not just possible, but repeatable and scalable. It might sound to you like science fiction, but it's already happening. I'm very excited to be talking today with Stef from Reditus Space. Stef, welcome to the show.
Thank you very much for taking time, and thank you for having me.
So tell us what Reditus does and tell us the origin story behind it.
Yeah, I mean, you said it partially better than I can do. But yeah, very fundamentally at Reditus Space, we're trying to build reusable satellites for zero-G manufacturing. At a very fundamental level, we believe as a company that a lot of products in a many multitude of industries can really benefit from being produced in the microgravity environment. Fundamental materials, not the actual products themselves, can just be made either more pure, better, or frankly, different properties or completely different materials to the alternatives that we can make on Earth we want to enable. So the thing from our side that we look at as a really potential where we can make a change is by enabling people to get to space, particularly and very critically here, get back more often.
And someone was asking me, like, can you explain it to me like I'm a 5-year-old? And I said, it's a big metal box that goes to space, and then there's some stuff being built inside, and then it comes back to Earth. Is that the right way to say it?
Yeah, I mean, exactly right. And then the idea is that subsequently it's able to go up again and again and again. But from the service that we provide, right, the whole YC environmental is you express the service that you provide to your customer. Very fundamentally from our side, it is we are a transportation company. We bring you up and then we bring you back. And we are just figuring out and working on a way to do that more efficiently than any of the current alternatives.
So we'll get to the alternatives in a minute because there's not that many and you're almost the only one. But first, let's double click for the audience on why zero-G manufacturing is interesting. You said some components could be done better. I actually think, correct me if I'm wrong, but or tell us more. I actually think some things can only be manufactured in space. Is that correct?
Yeah, so the really interesting ones, particularly at this point in time, just because the cost is still it's space, right? It's still quite expensive. The really interesting parts, at least in the short-term future for us, are producing the facilities where there's simply no alternative to create this on Earth. And so there's types of pharmaceuticals, there's types of materials where you cannot make these on Earth. It's just the disturbance of gravity and that perturbation during the production process is too much of an inhibitor to make that type of material. And so the best way that I've always found I can explain it to people is by referring back to high school chemistry, right? You go to your carbon structures and you go to, right, from all the way from graphite to diamond. Fundamentally, they are the exact same components to make the structure, but they are formed they're formed in a different process under different circumstances. And so gravity is also a factor in that same type of manner, where because you expose it to a different environment, different circumstances during its production, you can get a different result. And maybe in certain situations that isn't as dramatic as going from, right, your pencil to diamond, but it is different. And in certain situations, if that allows you to create certain properties that you otherwise can't have, that gives you a completely different result that can be incredibly valuable.
It is so relevant right now because I believe, again, you're more of an expert than me, but I believe that AI is allowing us now, only for the past few months, to discover new materials. Theoretically, we might discover some materials that we don't know how to engineer, but giving us another way of manufacturing new materials, which is you can manufacture on Earth with gravity or in space, which allows you to do more things, then it opens up AI to discover a whole set of new materials for us. Is that what's happening already?
I think to a certain degree, I mean, there's definitely I wouldn't say at least up to 25 years ago, there have existed a lot of theoretical models on, hey, what type of materials can you make in microgravity? I would speculate it started even longer ago, but I know for a fact that at least 25 years ago, people were already doing that. And then the big question has always been, right, doing that actual implementation. Getting things to space is really hard, particularly when you intend to get them back. And so the discrepancy between like physical implemented research versus theoretical models has always been really heavy on the theoretical model side with all of this research, just because it's a lot easier to do. It's much easier to spend 1,000 hours working on something on Earth than even 1 hour in space. And so this entire industry so far indeed is incredibly heavy in a lot of material models and simulations, etc. And so as a result, you certainly have a lot of now these AI applications that are starting to look at that exact same potential. Really interesting to see what they're already coming out with, because it's relatively new, but it's already generating very interesting results.
And you mentioned twice already, so I want to get your take on that. You mentioned that going up is not even the hardest. It's already incredibly hard for almost everyone. But actually coming back is the hardest. Could you expand on that as well?
Yeah, I mean, down mass in space is that's the general term that you would use for transportation from orbit back to the surface, has been very tricky for a long time. Obviously, it's something that we've done successfully a long time ago, right? The biggest initial missions that you can count to the Apollo program for those initial types of capsules that frankly haven't changed an incredible amount ever since. Obviously, it's gotten more advanced, but the fundamental concept still very much remains the same. But yeah, particularly now when you look at the distribution of how much goes up versus how much comes down, we are talking incredible amounts of launches, all for satellites that frankly are just intent to stay on orbit, either until they well, hit the orbit and evaporate, or they go into a graveyard orbit. But the result, either way, is that they do not come back. That's kind of the norm for almost everything. The exceptions to that within at least the majority of human history have been scientific missions, right? Think right NASA missions and other governmental space agencies who do things for the sake of scientific curiosity and exploration because they're trying to get materials back, right? They collect samples of like lunar samples, Mars samples, whatever else it might be, just to return them to Earth so we can analyze them here, which that so far has been one of the very few things that has been valuable enough to bring them back. That then kind of changed with the space station. All of a sudden, we started bringing people back, and then people can take some cargo with them. But those have kind of been really the only ways where you can do down mass. And still, frankly, down mass from the space station is still very tricky. And that's kind of the gap in technology that we see as a potential to bridge, because with an ever growing and thriving space economy, there is just that need for certain mobility, and we think space manufacturing is that application for it.
It's interesting. Even I never really thought about it. We always think of going to space and never of coming back. But yeah, we could probably argue that I don't know the number, but it's probably something like between 90 and even 99% of the mass that goes in space never comes back.
It depends if you count burning up on reentry as counting coming
Exactly.
back.
I
But
agree.
presuming that it isn't, then yeah, 99% of the mass never returns. Yeah, I was about to say that's a. Yeah, so not the actual fundamental semiconductors themselves. So I don't think we'll see any like large scale lithography machines in orbit anytime soon, but rather the semiconductor substrates. So, and there are, once again, as with many of this industry, right, there's a whole variety of applications. But the main ones that I would always point to are two. One are a lot of applications where people are making current type of infrastructures for semiconductors more pure, basically reducing the dislocation rate. So you have a more perfect semiconductor. The other one are just like looking into new type of materials, whether you then go into other types of composites, right, your diamond semiconductors, etc., or very quickly you start looking into new type of structures internally. Either way, it is about making new type of crystal structures that then can be transformed into semiconductor. Yeah, I mean, it's the fundamental material, right? And I think that that still very much is the starting to make anything. And I think it'll be a while before we start mass producing semiconductor substrates for data centers on orbit. I don't think the unit economics are there to support the production of those right now. But there are certainly a lot of niche applications that are frankly becoming much less niche, where you very quickly see that transition where a lot of those products are starting to make sense, especially as they're further and further in the maturity of their process. But yeah, no, but even just on the semiconductor side, there's companies that are very much now actively producing these on orbits, getting those results back, and right, we talk to them almost every day. Hey, they now right, have finally gotten to the stage where over the past couple of years they've flown their proof of concept. They're at a stage where they can show like, hey, we have made either a larger version or a more pure version or a completely different structure than anything we've been able to do on Earth over the past 15 years. We now just need to make more of it. One, we need more data points, or frankly, sometimes they just want to start selling them. The question is just they can't. Yeah, exactly. That is where we try to collaborate them and get them to space more. Yeah, so the other options, I would say 99.9% of current activity to date has happened on the International Space Station. It has, in that sense, been completely revolutionary. Right, 30 years ago, when they put it up first, it basically kicked off the entire stage where, while this hypothesis has existed for much, much longer, right? There have been people that have talked about doing this in the absence of gravity for I think the earliest documentations of theory go back almost 100 years. The actual application itself was basically never done because the research facilities just weren't there. The International Space Station did fully change that. And so for the past 30 years, that hypothesis of like, hey, we think that we can make better or different materials on orbit has, right, it existed for a long time. 30 years ago, we finally started to get some proof, but it was incredibly small scale. And it was always about, hey, we think that we can do this. Let's try and get some numbers behind that. Let's see what kind of dislocation rates can we get. And I think the really interesting turning point over the past couple of years has been now, hey, we know that we can make things better. Let's see if we can increase that quantity. Let's see if we can actually start getting to a point of commercialization and applying this in either industry or research. How can you do that now? I think the International Space Station has kind of remained the sole operator. A recent change over the past couple of years have been companies like Reditus Space, who've specifically done it for pharmaceuticals. And then there are a small couple of entities now as well. The big transition that we are about to live through is the International Space Station disappearing. The current set date for that, as of recent communication, still, as far as I know, is there's been some inconsistencies in the communication about that date, but that, as far as I know, that is still the plan. That means that by that point in time, the expected transition point is in a couple of years, the private space stations will take over. Your Axiom Space, your Fast Spaces, and a couple of other players are all intending on taking over that role that the International Space Station once played, but from the private sector. And I believe that a lot of those entities certainly have the interest of continuing that research and ideally scaling it up. Those are kind of your future intents, but that is kind of where it ends. That's your only locations to really get something back from space right now, if you're at least talking from the United States perspective. And so that is a really short list. And so if you're not in a situation where you actively have a route to getting to one of those locations, that's kind of where your game ends. And that is what we want to put a stop to. Yeah. By and large, if you want to go onto the International Space Station, there's a whole lot of routes to get on there. But the structure for the overwhelming majority of experiments is that it is a slot that has to be granted to you, meaning NASA, the NIH, or whichever government entity that has an allocation of some of those slots has to go, yes, we think that this is something that we want to fly, and so we will grant you transportation to the ISS, and then you can do there whatever you want. And then while you're on station, you can collaborate with some what are called implementation partners, think nanoracks, Redwire, etc. But the fundamental thing behind it is you need to be granted a slot by what is usually a government entity. That's tricky because it means that you can't just get, like, if you need 100 slots, you can't just get 100 slots unless you are something that is the utmost priority to NASA. You are just not going to get the frequency and the amount of volume that you're going to need. And so most people that are trying to create like large scale efforts, that is an incredible inhibitor. You just can't get there the amount that you want to. Right? You couldn't pay for it if you wanted to, and that's just a big problem. Yeah. Yeah, so I'll walk it back to when I met my co-founder first, which was about 4 years ago when we both started our PhDs. And so during that time, we got involved in the reentry sphere, right? Thinking about how do we make coming back from orbit a more efficient process? How can we look at that and go, hey, we've done it relatively the same way ever since the Apollo program. Like the materials might have gotten a bit more advanced, but fundamentally the system is still the same. How can we make that a better system? And so we did a good amount of research on a lot of topics, including that, over a couple of years. And we very quickly got to a point where, right after a couple of years, we had people approach us at conferences, etc., talking about this exact problem. Companies that were quite literally talking to us about, hey, I want to go to the space station more often. I am trying to pay people to get me there, and they just won't do it. There's no facility that will allow me to do this, which we thought was one of the craziest problems we'd ever heard. And so as the years went along, we actually originally thought of this problem, wanted to work for another startup that was solving this because we thought, fantastic. We think this is a really cool thing to work on. We want to work on this. Let's find someone that's solving this exact problem and see if we can work for that company. And then over the course of a couple of months, we looked around, right? We got close to the end of our doctorates. And so started looking for a spot to land after that. And we didn't really see any company that was solving it in a way that we thought made sense. Not just from an engineering perspective. We looked at that and we were like, you see some startups trying to tackle this, but not in ways where we're like, hey, that's the right way to do it. And that kind of led us to, hey, maybe we do this ourselves. And that kind of brought us to today. Yeah, I think the big thing that I always love to talk about, so that I would absolutely want to address, is we have our first mission. It is called the Enos mission, coming up. The launch window opens March 1st of 2026. And so on that mission, we will be carrying a payload that will be doing, amongst other things, pharmaceutical research, right, towards basically research towards commercialization of a pharmaceutical product. And we're incredibly excited about it. It'll be full scale orbital mission. It'll orbit for approximately 8 weeks. After that, it will activate its deorbit burns and return to Earth to be returned in most likely the Gulf. Yeah, approximately. Yeah, that's the goal. Yeah. It's a combination of a couple of things. The process usually involves a couple of weeks. And that is due to a variety of reasons, but mostly just because the manufacturing process actually takes much longer, at least than I expected intuitively. That is one factor in there. There's just a lot of like necessary maneuvers, etc., from our end. Unfortunately, you don't pop into space and start producing, at least not on the first one. And so we certainly have to plan in for some allocated time towards making sure that the system works before we start gearing up everything, that we know that we're in a stable and certain situation where nothing pops up to the effect that we need to, where we start manufacturing and then halfway through the manufacturing process we have to get put a halt to it because we're running in a power deficit or something of the kind. And so there's a lot. Yeah, it's we need to, just as a general philosophy, we need to make sure that the satellite is in a, what you refer to as a healthy position before you start doing a procedure that you cannot stop, that you basically only get one shot at. Exactly, right. There's just, particularly on the first one, there's just a lot of risk mitigation that happens. And so over time, that 8 weeks reduces to, call it three, maybe four. But at least for the first one, we want to make sure we get that. Exactly. They still have to wait a year now first before they get to launch, right? So they'll be all right. Yeah, you have to make things that are incredibly valuable. And so that's a lot easier to achieve single flights just because it's mostly, right, it's still proof of concept and research things. And so while we're in these stage with most of our customers right now going, hey, we've now verified this, we're trying to get it to market, there's a lot more flexibility in terms of those price points just because it's not about the unit economics yet, because it's still either proof of concept or initial demonstrations of manufacturing capabilities, etc. And so people are, right, willing to spend more on that than they would be on the actual production line, as with anything. The really interesting question that you did bring up from unit economics is, how does this convert into like large scale production, right? What if you're making the same thing continuously? Because that's obviously what we want to build to. And so that we look at as our piece of this whole puzzle, because we work with some incredible partners that are trying to push the envelope in terms of the type of product that they can make, but they need to get to space often and they need to get there quote unquote cheap. It's space, so everything's still expensive, but for relative terms, they need that price to come down and they need to be able to get there as often as they need for as low a price point as possible. And so the reason why we as a company decided, hey, we need to take fundamental ownership of the development of the satellite bus and development of the heat shield is because we aggressively pursue reusability. We believe fundamentally that reusability is the critical piece to allow this entire picture to take shape. If you are going to be forced to leave your satellite systems, your propulsion systems, your ADCS, sorry, I won't get too technical, your power systems and everything in orbit every single time, I don't believe that in the long term this is ever going to be financially feasible. We have to have the ability to go up and down without leaving over $1 million of space hardware on orbit. And so the only way that we believe we can do that is by making it reusable, and that's how we think we can make the unit economics work here. Yeah, yeah. Yeah, no, absolutely. I think we certainly stand at a point now where we very much made it a point where our business model stands perfectly by itself in the current era of fuel. Like we, with Falcon 9 prices and some of the alternatives, we are at a point where we can still fly and certainly operate without it. But yeah, we're incredibly excited about when we get to a point where Starship and some of the other competitors like Stoke Space start flying and getting to the full scale reusability, or frankly, just the absurd size that Starship is. Yeah, when you get to those types of points, those prices start dropping even further, which for us only unlocks additional customers, right? They're all of a sudden their business model starts to work. We can take up more people. It's obviously launch is a significant cost factor for us, and so being able to reduce that one is huge. No, absolutely. No, and I mean, I think launch is for every single space company an enormous cost factor. And so that drastically reducing, like it already has and is continuing to, yeah, I would be surprised if you can find a space company where that isn't huge. Yeah, I wouldn't even call it an unsolved problem, just something that we still look at as just, to be completely honest, incredibly tricky. And I think it'd be naive of us to not call it that, and that is reentry, right? You hit the atmosphere at approximately 5 miles per second. That turns everything, that quite literally turns the air in front of you into a hot plasma that can reach up to about 7,000 degrees Celsius and is pressurized enough where it is able to vaporize almost anything. Surviving that environment while fundamentally still keeping your system perfectly balanced and aimed at the right location such that it doesn't land just anywhere on earth but exactly where you is tricky, right? It's just saying that isn't an incredible engineering challenge would be disingenuous. And so, yeah, that's something that we've been building towards for the past 10-ish months of this company existing. And so we will continue towards it. And I have all of the confidence in the world that we are going to manage it and that the mission will be successful. But I would be lying to you if I said that wasn't something that I very actively think about. Yeah, that's right. Yeah, so you have what's called your thermal protection system, which is a very fancy word for saying we have like material that's coated on one side that is able to resist like the peak temperatures that you experience. But yeah, you only put that on one side, and so you want it to be like stable both passively and dynamically as it's doing its reentry. You want to have that side aimed down because if yeah, for some reason you flip, I think one you would continue to flip, and that causes a whole other slew of problems. But yeah, if you expose your belly, if you will, yeah, you would melt up.
I'm guessing it's not at all possible to put this material everywhere. What would be the consequences? And same question, are there other shapes? Yeah, that it's not a belly, but it's a very long spiky thing. Or can we get creative here?
You absolutely can. And so we people have an incredible amount, but it's been an optimization problem. I think is the best way to call it. You can most definitely put protective material around everything, but just your satellite will become much heavier, and yeah, it will become much
And
heavier and just
expensive.
less
Yeah.
efficient operation. Yeah, everything becomes more expensive and just more difficult to operate because all of a sudden you got to poke your radio through this protective. Things just become more tricky, and you could most definitely make an incredibly weird shape if you wanted to. If you wanted to make a bean shaped satellite, you could. I don't know why you want to though. It would be stable.
A lobster shaped satellite. Sorry, keep going.
Yeah, you could make it. You could make a lobster-shaped satellite, and it would like theoretically you could make it work. Probably has to be quite. I don't know if the a lobster does have a little bit too many like thin things poking out. That would cause you some problems, but it's about an optimization problem, right? You want your shape to account for as much volume as possible while protecting as little surface area as you can, while you want it to be stable. Because if it starts flailing around, that is incredibly difficult to model, but also it's just incredibly difficult to keep control of. And so By and large, I would say good rules to keep in mind when you go through this process is you probably only want one side facing the hot stuff, right? The plasma. Just because you only have to protect one half, which is just easier, it's more efficient. And so if you're going to do that, you need it to be stable, and then there's only certain shapes that are stable. A lot of other ones start flailing around when you start applying a little bit of perturbations. And
So it has to
so,
be has to
yeah,
be round necessarily, right?
it doesn't have to be round necessarily. Round is just a really easy shape to keep stable. And I think the best way to think about this is in terms of planes. You, by and large, want things to be really stable. So, like a large jet that we would fly on, like a regular passenger plane, is a really
Hmm.
stable thing, which is why it's a very nice flight. And that's what you want to
Hmm.
pursue. If for some reason you want like a really crazy amount of maneuverability, that is possible, but you need a lot of control
Hmm.
surfaces. That's when you shift towards a fighter jet. Those are technically not stable, but you have a lot of
Hmm.
control surfaces, and that's how you can make it work. Theoretically, you could do the same thing with a reentry device, but I would suggest to anyone that is trying to do the same thing to at least use a more stable version the first time, just because it makes life a whole lot
So
easier.
we'll scrap the lobster for now, but that's a fascinating
Lobster.
it's a fascinating problem to work on. I'm sure it's just so interesting. Thank you very much for that. And I want to ask you, if and when Reditus Space succeeds wildly, what changes for us about life on Earth?
Ideally, in our long-term vision, space just becomes another location for people to do the manufacturing of products that can then bring people a better life. Fundamentally, we want people to have the products that they, right, the materials that they can then use to, how do I describe this in the best way? In order for people to have the type of revolutionary products, we need to just have a manufacturing line where we can continuously bring things to space and back. And that should be almost equivalent to having to transport things to a different country to have them be manufactured. It's just that this country or this site where you can do manufacturing happens to not have any gravity available to it. We want to do that because it allows people to make the type of pharmaceuticals, the type of materials, and the type of a bunch of other products that they need to make life better, right? You want people to not have to worry about certain heart conditions because this revolutionary type of drug has been made in space to alleviate the problems that come with that condition. You want people to use the new greatest type of AI because the new type of semiconductor substrates have been manufactured in space. You want people to have even faster internet than they can because the new type of optical fibers have been made in space. When we really get into the future, the big thing that I always look at as the holy grail to work towards, which we haven't talked about yet, but I really recommend that people look into it, is organ manufacturing. We try to not put it too front and center because it is still relatively far away and frankly incredibly sci-fi. But there has been an incredible amount of research done in people quite literally manufacturing and 3D printing. It's not really 3D printing, but something like it, body parts and organs on orbit. And that's something that I really look at as a long-term potential that is incredibly interesting.
It's fascinating because I did read about 3D printing, quote unquote, of organs. And I also remember
Mhm.
people saying that one of the biggest issue is gravity, because the organ
Yeah,
is a lot of different parts in a lot of different ways. I never actually made the jump or the link with zero G manufacturing, but it's the perfect one.
it's technically the same industry if you want to pull them together that way. And so it's an incredibly interesting one because obviously news headlines make it seem like people are actively printing full scale
Yeah,
hearts on orbit. That's not really what's happening yet. But I would say the biggest inhibitor to that industry as well is just the access to the microgravity
yeah,
environment, not being able to run a whole lot of tests, right? If you're able to run a test every 18 months, your progress is just going to be
yeah.
slow. And so that's really what we want to put a change to. And yeah, we're not printing full scale lungs anytime soon, but it is certainly, I believe, in our
Yeah,
future.
I can see a future in both our lifetimes where you have a lung, heart, whatever problem. You go into a lab And I think you just need to do a saliva swab, right? Because from any cell now you can create a stem cell that goes into space. You go home, you can look at the sky. You don't see it, but you can imagine the satellite going over your head a couple times. And then a month later, when you re-entry, and then you go back to the lab, to the doctors, and boom, your heart is here, your lungs are here. Something new has been literally manufactured for you in space. Isn't that crazy?
It's insane to think about, but it's, I think, a lot closer than most people will
I
imagine.
agree. I agree. That's awesome. That's so exciting. I'm so pumped right now. Okay, I do have to let you go in a couple of minutes. I wanted to ask you maybe two more questions. One is, what is something that you believe about the future of space that very few other people do believe as well? Something counterintuitive, or that you're almost the only one to believe?
I think, and this is not a fun opinion in this sense, because I always want it to be not true, but I think that the future of the majority of space operations will take place without people in it. I think one of the most impressive things that we've done, by and large, in the entire spaceflight industry, frankly, mostly by government agencies again, is keeping people alive in space.
Yeah, that's true.
People are incredibly challenging to not kill, and it's so incredibly high stakes that everything involved with people fundamentally becomes so much more of a burden that I look towards the future of one, deep space exploration, but even just operations around Earth orbit. And I personally expect that, borrowing the space tourism sector, if you will, the majority of the development in the space industry will continue to take place without people.
It's interesting. I agree with that very much because of AI and robots and stuff, how challenging it is. But also comes to mind immediately the fact that we need to establish human presence on other planets in case something happens to Earth. We need probably a colony on Mars. And it's at the same time, it's so impractical. It would be so much better and easier to just send robots. So I don't know how those two things are
Now,
going to clash in the future. That's going to be interesting.
it's a certain, at that point, yeah, you run into certain parts where maybe humans do play that role, but I think they become ever less functional, if that makes sense. At a certain point, a lot of those complex operations, like things involving
Hmm.
hands, etc., you simply needed to have people for, because we couldn't think of a different way to
Yeah.
do them. I think that need is ever decreasing. And so I think in a lot of functional systems, particularly ones that have to be optimized, people become less useful. But yeah, there will always be a place for people, indeed, in things like Martian
Hopefully.
colonies and space tourism.
Yeah.
But yeah, people are growing, are working on
Yeah.
alternatives, and I think that's incredibly exciting because it unlocks a whole host of new things.
Interesting. Yeah. Very cool. Okay. Is there a book that you could share with me and with us that had a big impact on your life? A book that you read or gifted a lot, but that you'd like to share with us today?
One that I generally always really like to think about in these types of situations, I read it, I want to say, a couple of years ago, is Humankind: A Hopeful History
Okay.
by Rutger Bregman.
All right. Is that about space?
It is not about space at all. It's a general, a slightly more optimistic view of reality or of people than we get these days.
Okay. Very cool. I got it here. I'll check it out. Thank you so much for being here. If listeners here want to stay in touch with you, follow what's happening, what's the best way to keep up with Reditus Space and with you?
The best way to keep up with Reditus Space and myself are probably on X as well as LinkedIn, or make sure to check out our website. It's very easy, reditus.space.
That's awesome. Stef, thank you so much for coming. I had a blast. I hope you had too.
Thank you very much for having me.
And to our listeners, if you're still here, thank you so much for listening until the end. Please give us a 5-star rating on your favorite podcast app. If you're on YouTube, you can watch us. It's even better. Hit the notification bell and the subscription button, and I'll see you in the next episode. Bye, everyone.